Good morning friends, we are going to discuss about the numerical of exercise of chapter 15 waves. Up to the 15.6 numerical of exercise we completed with the discuss. Now today we are going to discuss about the 15.7, 15.8 and 15.10 numerical of exercise. Now 15.7. A hospital uses an ultrasonic scanner to locate tumors in a tissue. What is the wavelength of sound in the tissue? In which the speed of the sound is 1.7 km per second. The operating frequency of the scanner is 4.2 megahertz. Now listen, in hospital, the ultrasonic scanner is used to locate the tumors in a tissue. What is the wavelength of the sound in the tissue? Right? In which the speed of the sound is given the 1.7 km per second. The operating frequency of the scanner is 4.2 megahertz. Where is it numerical? That may be asked for the 1 marks question in good set and also the NEET and competitive exam. Now listen here. What is the first is given? The speed of a sound wave in tissue V is given 1.7 kilometer per second. Convert into meter per second, that means the 1.7 into 10 is to 3 meter per second. Now, the operating frequency of the scanner is given, F is equal to 4.2 megahertz. Convert the megahertz into hertz, therefore 4.2 into 10 is to 6 hertz. We had to find out the wavelength of ultrasonic sound in tissue. So where is it numerical? Also we know that the speed of a sound wave V is equal to frequency into wavelength. Therefore, speed of a sound wave V is equal to F lambda. We require the lambda, therefore V upon F. V is already known, that is the 1.7 into 10 is to 3 upon operating frequency 4.2 into 10 is to 6. So as we simplify, so that is the 4.047 into 10 is to minus 4 meter. So that is the wavelength of ultrasonic sound in the tissues. So very short numerical. That is the most important for objective type question in competitive exam. Standard equation V is equal to F lambda we are using. Here in question, the speed of a sound is given in tissue, that is the 1.7 km per second, convert into meter per second, therefore 1.7 into 10 is to 3 meter per second. And now, the scanner of the ultrasonic wave is operated at the frequency 4.2 megahertz. So frequency is 4.2 megahertz. Convert into hertz, therefore 4.2 into 10 is to 6 hertz. So what should be the wavelength of this ultrasonic sound in tissue? Therefore, we know the equation of speed of the sound wave. V is equal to F lambda. So from this equation, lambda is equal to V upon F. V is already 1.7 into 10 is to 3 and F is 4.2 into 10 is to 6. As we simplify, we get the wavelength is 4.047 into 10 is to minus 4 meter. Here is okay. Now next, 15.8. A transverse harmonic wave in a string is described by the equation yxt is equal to 3 sine 3060 plus 0.018x plus pi by 4. So harmonic wave is represented by this equation, where the x and y are in centimeter and time t is in second. The positive direction of x is from left to right. Now, first, is this traveling wave or a stationary wave? So what is the equation of the transverse wave given in this string? This wave is traveling or the propagating or stationary wave. First we have to decide this. If it is traveling, so what is the speed and direction of its propagation? Suppose we give the answer, this equation represents the wave. This wave is traveling wave. So we have to find out what is the speed of this wave and in which direction this wave is at present traveling. Now B section. What is the amplitude and frequency of the wave? We have to also find out the amplitude and frequency. And third, what is the initial phase at origin? That means at initial, that means the time t is equal to 0, and at origin x is equal to 0. What is the initial phase of the wave? And last is, what is the least distance between two successive crests in the wave? The minimum distance between the 2 points at which the successive crests are formed. For that purpose, first the given equation is compared with the standard transverse harmonic wave. Right? The given equation is y xt is equal to 3 sine 36t plus 0.018 x plus pi by 4. Comparing with our standard equation, y is equal to a sine omega t plus kx plus phi. So we get a amplitude A is equal to 3 centimeter, omega is equal to 36 radian per second, and K is equal to 0.018 radian per centimeter. And phase phi is equal to pi by 4 radian. Right? So this type of the information we obtain from the given equation as we compare with our standard equation. Now answer the first question. The given equation is one-dimensional traveling harmonic wave. Right? Propagating along, here x is positive, therefore that is propagating in minus x direction. Right? The given equation is one-dimensional traveling harmonic wave propagating along minus x direction. Because in first part, first we have to decide there is the traveling or the stationary wave. We say that by comparing with this, so there is the one-dimensional traveling harmonic wave. So in which direction there is propagate? There is propagate along the minus x direction, because its form matches with the standard equation y is equal to a sine omega t plus kx plus phi. Now, what is the speed? Therefore, speed v is equal to omega upon t. Omega already we found 36, k is this, therefore 36 upon 0.018. Thus we obtain 2000 centimeter per second, or in other words 20 meter per second. 20 meter per second. So that is the answer to the first part. Now in B part, what is the amplitude and frequency? What is the amplitude and frequency? Second B, amplitude A is equal to 3 centimeter. Omega is equal to, already we obtained the omega, 36 radian per second. Omega is equal to 2 pi f is equal to 36. Therefore, f is equal to 36 upon 2 pi. 36 upon 2 pi. Therefore, 5.733 hertz or the second inverse, that is the frequency. 5.733 hertz or second inverse, that is the frequency. Now, C part, what we have to find out, the initial phase at origin. For initial phase at origin, for initial phase at origin, take t is equal to 0, x is equal to 0 in theta is equal to omega t plus kx plus phi. Therefore, theta is equal to pi is equal to pi by 4 radian. That is the initial phase. Because this part represents the initial phase. This part represents the phase at time t and at position x. But we require the initial phase, that means that at time t is equal to 0 and at origin, that means the x is equal to 0. Substitute the t is equal to 0, x is equal to 0, we obtain the pi is equal to pi by 4 radian, that is the initial phase. Now, the list the distance between two successive casts. We know that between the two successive casts, the distance is equal to wavelength lambda. Lambda is equal to 2 pi upon k. Now, section D, list distance between two consecutive casts. Lambda is equal to 2 pi upon k. 2 pi upon k. Substitute the value 2 pi 3.14, k is 0.018. Thus we obtain 348.9 centimeter. 348.9 centimeter. That is the distance between the two consecutive casts in a wave. Again, actually very easy numerical. Here the given equation. If this type of the equation given, we have to find out the frequency, amplitude, initial phase, speed. So first we have to compare with our standard equation of the wave. Right? So given equation is yxt is equal to 3 sine 36t plus 0.018x plus pi by 4. Compare with y is equal to a sine omega t plus kx plus pi. We obtain the a is equal to 3. A is equal to 3. Now omega is equal to 36. K is equal to 0.018 and pi is equal to pi by 4 radian. Right? Now this is this standard equation is the equation of a one-dimensional progressive harmonic wave propagating along the minus x direction, because the x is equal to here the plus, x is plus. Therefore, our given equation is also in the same form. So, according to our first part A question, this wave is traveling or stationary. So, answer is that given equation is one-dimensional traveling harmonic wave, propagating along minus x direction. Because its form is matched with y is equal to a sine omega t plus kx plus phi. If there is a traveling, so what is the speed of this wave? What is the speed? And direction. Direction is minus x. Okay. Now the speed v is equal to omega upon k. Omega and k are already known. 36 upon k 0.018, therefore 2000 centimeter per second, therefore 20 meter per second. That is the speed of a sound wave, the given wave in given medium. Now next, what is the amplitude and frequency? Already we find out the amplitude is 3 centimeter. We have to find out the frequency. We know the omega is equal to 36 radian per second. Omega is equal to 2 pi f. So 2 pi f is equal to 36. Therefore f is equal to 36 upon 2 pi. Therefore f is equal to 5.733 hertz for the second inverse. Now next, see. What is the initial phase at origin? Initial phase. Equation of the phase theta is equal to this. Theta is equal to omega t plus kx plus phi. At origin and at initial position, take the t is equal to 0, x is equal to 0 in. Theta is equal to omega t plus kx plus phi. Therefore, phi, theta is equal to phi, and phi already we obtained, that is the pi by 4 radian. Therefore, initial phase at origin is pi by 4 radian. Now d pi, what is the least distance between the two successive crests in the wave? First the crest according to this figure. The point of the medium at which the maximum displacement occurs. These 2 points are known as the two consecutive crests. The distance between the two consecutive crests is always lambda. Therefore, lambda is equal to 2 pi upon k. Now 2 pi 3.14 k already we found 0.018. Therefore, 348.9 centimeter is the wavelength. Here is okay. Now the next 15.10, 15.9 is cancelled. Now then, for the traveling harmonic wave is given y xt is equal to 2 cos 2 into bracket 10t minus 0.08x plus 0.35. Right. Calculate the phase difference between oscillatory motion of the 2 points separated by the distance a 4 meter, b 0.5 meter, c lambda by 2 distance, and d 5 lambda by 4 distance. First, the given equation yx is equal to 2. That is given in cos form. 2 is outside the bracket, we take the inside. Therefore, 2 into 10, 20 minus 8 into 2, therefore 0.016 x plus 0.35 into 0.7. Right. Calculate the phase difference between oscillatory motion. For that purpose, this type of the equation given, we compare with our standard equation. So given equation is this, compare with y is equal to a cos omega t minus kx plus phi. Therefore, we obtain the k is equal to 0.016 radian per centimeter. We only require the k. Because we have to find out the phase difference. Phase difference at any point is delta is equal to k into x. Delta is equal to k into x. Now, in the direction of propagation of a wave, phase difference between two particles is delta is equal to kx. Delta is equal to kx. First for x is equal to 4 meter. Delta is equal to k 0.018, 0.016 into x 4. That is given in radian per centimeter, therefore x is taken as the centimeter. So it's equal to 6.4 radian. 6.4 radian. Delta. Now, second B for x is equal to 0.5 meter. 0.5 meter. Therefore, delta is equal to kx is equal to 0.016 into 0.5 meter, that means the 50 centimeter, is equal to 0.8, is equal to 0.8 radian. Now, for C, at x is equal to lambda by 2 distance, lambda by 2 distance. Therefore, delta is equal to kx, k is equal to 2 pi upon lambda, 2 pi upon lambda. X is equal to lambda by 2. Therefore, 2 upon lambda, lambda by 2 cancel. Therefore, delta equal to pi radian. And D, at what distance given? Pi lambda by 4. Therefore, delta is equal to kx. Therefore, delta is equal to 2 pi upon lambda into pi lambda by 4. Pi lambda by 4. Lambda, lambda cancel. Here 2 cancel. Therefore, pi by 2. Pi by 2. Pi by 2 radian. Now, the phase difference between the 2 points in the direction of the propagation, taking the part of propagation, is delta is equal to k into x. K is the wave vector, x is the distance between them. Okay? For that purpose, for the dialing harmonic wave is represented by yxt is equal to 2 cos 2 into bracket 10t minus 0.008x plus 0.35. Calculate the phase difference between oscillatory motion of the 2 points separated by a distance of first 4 meter, second is 0.5 meter, third lambda by 2 distance, and D 5 lambda by 4 distance. Okay. So first the given equation we have in that form, yxt is equal to 2 cos. 2 is taken inside, therefore 2 into 10, 20t multiplied 0.08, therefore 0.016x plus 0.35 multiplied with 2, that means the 0.7. Compare this equation with standard equation of the wave. Y is equal to a cos omega t minus kx plus phi. Here the harmonic wave is given, instead of the sign, is given in form of a cos. So we only require the wave vector k, not we require the amplitude omega initial phase, because we want to only find out the phase difference. Therefore, k is equal to 0.016 radian per centimeter. Now, in the direction of propagation of a wave, the phase difference between two particles is delta is equal to kx. Using this equation, delta is equal to kx 4, x is equal to 4 meter. Delta is equal to kx, So delta K 0.016 into X. X required in centimeter, therefore 400 centimeter, therefore 6.4 radian. Now B, for X is equal to 0.5 meter. 0.5 meter is equal to 50 centimeter, therefore delta is equal to Kx. Value of K 0.016 into 50, therefore 0.8 radian. Now, last two cases are given. Note the distance is given in meter. That is given in form of lambda. So first the lambda by 2 distance. Therefore, at X is equal to lambda by 2 distance, delta is equal to Kx. At that time, we are using the value of the K is not 0.016 radian per centimeter. We are using the equation 2 pi upon lambda. Therefore, lambda cancel, 2 to cancel. At lambda by 2 distance, the phase difference is pi radian. Now last is pi lambda by 4 or 3 lambda by 4. So delta is equal to, at pi lambda by 4 distance, this delta is equal to Kx. K is equal to 2 pi upon lambda and X is equal to pi lambda by 4. Therefore pi by 2 radian. That is the phase difference. Clear this? Okay.